And we're back to wrap up 19.3, where we're dealing with the strength of acids and bases. In the first podcast of this section, we took a look at the difference between strong acids and weak acids, and now we're going to take a look at the difference between strong bases and weak bases. Like strong acids, strong bases, and let me go ahead and get my pen, there we go. Strong bases will fully ionize, or in some cases dissociate, in water. For example, if I put sodium hydroxide into water, so I'll say that it's AQ, and if I had 100 of those, virtually all 100 of them will split up into sodium ions and hydroxide ions. I'll get 100 of these and 100 of these, and none of the NaOH will be left. Now, what are my strong bases? Basically, any group number 1 or number 2 hydroxides. Which group number 1 and group number 2? On the periodic table, meaning group 1 meaning the alkali metals. Any alkali metal with hydroxides such as sodium or potassium, lithium, rubidium, cesium, etc., those are all group 1 hydroxides. Those are all strong bases. Similarly, group 2 such as calcium hydroxide, barium hydroxide, etc., if it's a group 2 hydroxide, it will also be a strong base. Now, weak bases would be any of the other bases. And the weak bases are only going to partially ionize in water. For example, if I take some generic base, we'll just say B, and you put that into water. Alright? We'll say this is AQ, this is a liquid. Because this is a base, it's going to accept a hydrogen from the water. And so what you're left with, and we're going to say that this is in equilibrium, what you're left with is a base that has the extra hydrogen attached to it, which includes that positive charge. And in terms of the water, it's lost its hydrogen, so now it's a hydroxide ion. Alright? Well, what are some common weak bases? Well, the main one that you need to know, there are lots of them, but the main one that you need to know is ammonia. Ammonia is an incredibly common weak base. It's one of the top 5, maybe 10 compounds produced worldwide every year, so it's something that you should be aware of. Now, once again, you shouldn't try to memorize all of the calculations. All I really want you to know with weak bases is, can you put them in order of strength? Because if you have a weak base, you have an equilibrium situation. You can write an equilibrium expression K equaling the conjugate acid times the hydroxide divided by the original base. Of course, you leave the water out because it's a liquid, and this would be called the base dissociation constant, so we would call it Kb. Ka, Kb, Kw, they're all going to be the same in terms of the fact that they are simply just an equilibrium. Now, weak bases have small Kb's. That's what makes them weak. If they had large Kb's, they would lie far to the right and make them strong. But when you're dealing with these weak bases, again, the larger the Kb, the stronger the base is. So, if I give you a list of weak bases, you should be able to put them in order of strength. Number 1 being the strongest, number 5 being the weakest. If you want to pause the podcast and give it a shot on your own, that'd be fine. Okay, so looking at the KBs, which one is the largest? Well, 10 to the negative 4 is the largest exponent that we have, and you have 2 of them. This one has a larger first term, so that's going to make that the strongest. This would be the second strongest. The smallest KB is this 10 to the negative 10, so that's going to be the weakest one of these 5, so we'll say that that's the 5. The next weakest would be this 10 to the negative 9. And the one in the middle is the 10 to the negative 5. All right, so that would be in order of strength. So what you have to realize in terms of strong and weak acids and bases. Strong acids and bases fully ionize or fully dissociate, while weak ones do not. And in fact, the weak ones only do it on the order of about 1%. When you're looking at weak acids or weak bases, you should be able to put them in order of strength. The larger the Ka or the Kb is, the stronger the acid or base is. And the opposite is true. The smaller the Ka or Kb is, the weaker the acid or the base is. All right. In 19-4, we're going to take a look at neutralization reactions. This concludes 19-3.